Hi everybody, Mrs. Pesic here. We are looking at section 4.7, transforming exponential and logarithmic functions. And the learning objectives today are to transform exponential and logarithmic functions by changing their parameters, and to describe the effect of changes in the coefficients of exponential and logarithmic functions. So let's take a look at this chart. I think all of this is going to be familiar to you. Vertical translation, horizontal translation. I think all of this is going to look familiar to you. Vertical translation, horizontal translation, and so on. If you add a constant to a function, you're going to shift it up or down. If you add or subtract a constant to the x itself, for every x in the function, you're going to shift it to the left or right. You know all about these, but the point of this little chart is to show you that it will work the same with exponential functions. So if we have, for example, 2 to the x as our parent function, and then we write 2 to the x plus 3, as in this example right here, okay, that will be a shift of 3 units up. If we have 2 to the x minus 6, that's going to be 6 units down. If we have something subtracted inside like this, so 2 to the x minus 2, where 2 is being subtracted from the x, that's going to be a shift 2 units to the right. If we have 2 to the quantity x plus 1, that's going to be a shift of 1 unit to the left, and so on. You know, if we multiply a function by some constant a, we will have a vertical stretch or a vertical shrink. So here's some examples here. 6 times 2 to the x is going to be a vertical stretch. 1/2 times 2 to the x is going to be a vertical compression or vertical shrink. And then if we take 1 over b times x, that's going to be a horizontal stretch or a horizontal compression. So 2 to the 1/5 x is actually going to be a horizontal stretch by a factor of 5, and 2 to the 3x is going to be a horizontal shrink by a factor of 1/3. And then lastly, to reflect, if you have a negative f of x, that's going to reflect across the x-axis, and if you take the opposite of every x value in the function, then it's going to be a reflection over the y-axis, and you could do that with exponential functions also. Okay, let's take a look at this example. We're going to make a table of values and graph g of x equaling 2 to the x plus 1, and you're going to describe the asymptote and tell how the graph is transformed from the graph of the original parent function, f of x equaling 2 to the x. Well, if we plug in these numbers into this function right here for x, we will have numbers such as, if we plug in -3, 2 to the opposite of -3 is going to be 2 to the positive third, which is 8. Plus 1 is going to be 9, so we're going to have 9 here. And if you plug in a -2, you're going to have a 2 to the positive 2, that's 4, plus 1 is 5, and so on. 2 to the -1, that's 1/2, plus 1, that's going to be 1.5. And if I plug in 2, I get 1/4 plus 1, that's 1.25. And if I plug in 3, I'm going to have 2 to the -3 plus 1. That's 1.125. All right, so what kind of transformation was this on this function? Notice here with the negative x, that's indicating that we have a reflection over the, can you tell me? If you make all the x's opposite, it's going to be a reflection over the y-axis. So this is going to be reflection over the y-axis, and the plus 1 is going to be a shift up 1 unit. All right, so when we plot the points that we have, 5 and so on, and we basically get a graph that looks, I'll do my best, looks something like this. Oh, wait, that's not good. That's the best I can do with the technology I have right now. All right, so the domain for this function, how far left does it go, how far right does it go? For our domain for our function, we would say all real numbers. And for the range, it's how low does the graph go, how high does the graph go. And I think what we're going to see here is that there is going to be a horizontal asymptote, that the graph gets closer and closer to right here at y equals 1. So I'm going to even fill that in right now. Horizontal asymptote is y equals 1, and the range then is going to be from 1 to positive infinity, not including the 1. So that's why we use a parentheses with the 1. Alright, so that's how you do a graph of an exponential function. Okay, so here's your first notes must do. Alright, you are going to graph this exponential function, find the y-intercept and the asymptote, describe how the graph is transformed from its parent function, which the parent function is 5 to the x. So if you want to fill in this row first, you could. That's going to be the parent function. And then h of x, what you're going to put down here, is what you get when you plug in these x values into this function. Then go ahead and plot the graph as best you can. And tell me what's the y-intercept, what's the asymptote, and what kind of transformation was going on. Alright, when you're done with that, notes must do. Go on to watch the rest of this video. Okay, logarithmic functions can be transformed also. You can stretch, reflect, translate, etc. The parent function would be log to the base b of x. So let's take a look at this chart. This is just, again, summarizing all the ways that you can transform logarithmic functions. There's no surprises here. If you add some constant to a function, it's going to be a shift up or a shift down. But if you add or subtract something inside the parentheses before you plug it into the function, that's going to be shift right or left. If you multiply a function, a logarithmic function, by a constant, that's going to stretch or compress, like these examples. If you plug in a number times the x, then you're going to have a horizontal stretch or a horizontal shrink. And then if you take the opposite of the whole function, that's going to be a reflection across the x-axis, like y equals opposite of log x, that's a reflection. And if you have f of negative x, for example, y equals log of opposite of x, that's going to be a reflection across the y-axis. Okay, so just a quick reminder on how you would graph a logarithmic function. Let's say we wanted the parent function to be y equals log to the base 2 of x. That parent function, if I was to make a quick chart here, if I plug in 0, that's undefined, because 2 raised to what power gives me 0? Nothing. But if I plug in 1, I can say 2 raised to what power gives me 1? Well, 2 raised to the 0 power gives me 1. What if I plug in 2 for x? 2 raised to what power gives me 2? That would be 1. If I plug in 4, log to the base 2 of 4, that's saying 2 raised to what power gives me 4? That would be 2. If I go up to 8, log to the base 2 of 8 is equal to what? That would be 3, because 2 to the third is equal to 8. And so if I plot these points, 3 is here, and the graph actually looks, doing my best here, actually looks something like this. All right, now logarithmic functions, let me back up for a minute. We did a graph for an exponential function here, and we said it had a horizontal asymptote. But a logarithmic function is going to have a vertical asymptote. Vertical asymptote here is x equals 0. All right, so every logarithmic function will have a vertical asymptote, and in this case it's x equals 0. All right, to find the equation of the vertical asymptote for any logarithmic function of the form a times log of bx minus c and then plus d, all you need to do is set bx minus c, that's the part in the parentheses, equal to 0 and solve. The asymptote is going to be x equals that number. All right, so on this one, graph the logarithmic function, find the asymptote, state the domain and range, describe how the graph is transformed from the graph of its parent function. This is a natural log function, which means it's base what? Base e. And the parent function would be just, say, y equals ln of x. And for this transformation, since it's a negative x plus 2 in parentheses, I suggest you think of this as opposite of the quantity x minus 2. Isn't that the same? If I distribute this negative, I will get negative x plus 2. It's easier to think about what the transformation is if you have x minus 2 in parentheses. That tells us that it is a shift right 2 units. And then since there's an opposite in front, that tells me that there's a reflection over the y-axis. So those are the two transformations we have going on here. To find the asymptote, we would set this whole parentheses equal to 0. So we would do negative x plus 2 equals 0. And if I add x to both sides, I get 2 equals x. And that means my vertical asymptote is going to be at x equals 2. So vertical asymptote is going to be right here. All right, so let's get an idea of what this graph looks like by going to the calculator. If we go to the calculator, we want a graphs page, and we want ln, which we can get control e to the x gives us ln, and the graph was negative, parentheses, negative x plus 2. So I want negative x plus 2, and there's our graph. So we can see that it has been reflected over the y-axis and then shifted 2 units to the right. So on our graph, if we were going to graph that here, we could graph the vertical asymptote here, and our parent function was looking something like this. We want to reflect it over the y-axis like this, and then shift it 2 units to the right. So the graph is going to look something like this. All right, domain here would be negative infinity up to positive 2, and the range would be still negative infinity to positive infinity. All right, write the transformed function when f of x equals log x is translated 3 units to the left and stretched vertically by a factor of 2. Well, you know if it's stretched vertically by a factor of 2, you're going to have a 2 out in front of the logarithm, right? So it's going to be 2 times log of, and we want to shift it 3 units to the left, so we would need to have x plus 3 in parentheses. Okay, let's look at this example. Write the transformed function when f of x equals 4 to the x is translated across both axes and move 2 units down. Well, if it's translated across the x-axis, you would put an opposite in front of the whole thing. If it's translated across the y-axis, you would make the x negative. So we need to do both of those things. So we have opposite of 4 to the negative x, and if it's moved 2 units down, we have to subtract 2 from the whole function. Let's take a look at one last example. Write the transformed function when f of x equals ln of x is compressed horizontally by a factor of 1/2 and move 3 units to the left. If we're talking about a horizontal compression, that means you really need to multiply the x value by the reciprocal of this. So it's going to be g of x equals ln of 2 times x, but it's being moved 3 units. So we would have ln of 2 times the quantity x plus 3. Check me on that one on your calculator. That's it for this lesson. I hope you took good notes and you did your notes must do, and we'll see you next time.